I'm not mathematically gifted. And so there are all sorts of scientific and mathematical claims that I can't evaluate.
Yeah.
Pareto. This old client of mine, he was about 85 when he came to see me, and he was a financier and a kind of a mathematical genius. He made these little pendants out of a mathematical symbol for the most beautiful mathematical equation that was ever written. He made them out of gold, and he would hand those out. And he had studied psychology as a young man, and he introduced me to this concept that I didn't know about called the Pareto distribution. Pareto distribution. Pareto distribution. Pareto distribution. Pareto distribution. Pareto distribution. It's called a Pareto distribution. P-A-R-E-T-O. 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 Distribution. Pareto. Which, see, I'd been taught as a psychologist that most human characteristics were normally distributed, right? So most people were average and some people were extreme. That's a Pareto or a normal distribution. Okay, so we already talked about what a normal distribution looks like. That's the red line. And a normal distribution emerges as a consequence of chance processes. Performance among human beings is not normally distributed. A normal distribution is a distribution where most people are in the middle and there's a few people at the edges. And intelligence is like that, and height, there's more people of average height than very tall or very short, and weight is like that. And lots of things are normally distributed, and psychologists tend to assume that everything is, but it isn't. Creative products are distributed in a Pareto distribution, and that's a whole different thing. All right, so here's a Pareto distribution. This is the distribution. Remember I showed you with the creative achievement questionnaire that almost everybody stacked up at 0? People have 0 creative output. The median person has 0 lifetime creative output. And then there's a tiny proportion that are way the hell out on the right-hand end of the distribution, right? Those are the people everything is cycling forward for them. And as they get more well-known, of course, they get more opportunities as well.
The Pareto distribution is one of the simplest and most elegant examples of a long-tailed distribution that follows a power law. It is not a single curve, but a family of distributions, all related by a simple tail formula. The probability of seeing a value larger than x equals x min divided by x raised to the power alpha. Every member of this family is described by 2 parameters. First, x min, the scaling parameter. It sets the lowest possible sample value. Nothing can ever fall below it. That means there's no stacking up at 0, a point Jordan Peterson repeatedly gets wrong. In many cases, x-min is simply treated as a unit and set to 1 for convenience. Then alpha, the shape parameter. It controls how heavy the tail is, and determines almost everything about the distribution's behavior. When alpha is small, the tail decays slowly and a few very large values dominate the total. When alpha is large, the tail decays quickly and the distribution is more balanced. Starting from that tail formula, we can write down the standard functions of the distribution. The cumulative distribution function, or CDF, gives the probability of finding a value below a given level. It starts at 0 at x-min and rises smoothly to 1 as x increases. The probability density function, or PDF, is the derivative of the CDF. It shows how much probability is stacked at each value, and since Pareto follows a power law, this density itself falls off very quickly in the tail. And finally, the quantile function, or inverse of the CDF, goes the other way. It tells us which x value corresponds to a given level of probability. That quantile function will matter later, because it links the shape of the distribution directly to sorted samples, what statisticians call order statistics.
You can calculate an index called the Gini coefficient. And the Gini coefficient is a number that represents how much inequality of income distribution there is in a given geographical area.
The Lorentz curve is one of the classic ways to visualize inequality. On the horizontal axis, we plot the cumulative share of the population, starting from the smallest values and moving upward. On the vertical axis, we plot the cumulative share of the total held by that portion of the population. If everyone held the same amount, the Lorentz curve would be a straight diagonal line from 0 to 1. But for unequal distributions, the curve bends downward. and the more it bends, the more concentrated the total is at the top. For Pareto distributions, this curve follows directly from the power law tail. Smaller alpha means heavier tails, more bending, and greater inequality. The Gini coefficient measures the area between the Lorentz curve and that diagonal line of equality. A Gini of 0 means perfect equality. A Gini of 1 means everything is concentrated in a single point, perfect inequality. For Pareto distributions with alpha greater than 1, the Gini coefficient equals 1 divided by 2 times alpha minus 1. As alpha grows, Gini shrinks. As alpha approaches 1 from above, Gini approaches 1 from below. This ties the shape parameter alpha directly to a geometric, visual, and widely used measure for inequality.
Thing. And it's really important to know this. It's another fundamental fact, the knowledge of which can sort of transform the way you conceptualize, let's say, the political landscape. So here's an example of the Pareto distribution. You know, there's a rule of thumb that if you run a company that 20% of your employees do 80% of the work, or that 20% of your customers are responsible for 80% of your sales, or that 20% of them are responsible for 80% of the customer service calls. Same thing.
The famous 80-20 rule is often treated as if it were a universal law of nature. But in reality, it's just one special case of the continuous family of Pareto distributions. From the Lorentz curve, the share held by the top fraction of the population equals that fraction raised to the power of 1 minus 1 over alpha. If we set the top fraction to 20% and the share to 80% and solve for alpha, we get one specific number. Alpha equals the logarithm of 5 divided by the logarithm of 4, roughly 1.16. That's the only value of alpha for which the 80-20 rule holds exactly. Other values give different splits, 90-10, 70-30, or any other value you want to choose. So the rule isn't a rule at all. It's just one point on a smooth continuum of possible distributions.
Same thing, but that's not exactly the rule. The rule is worse than that. The rule is, in a given domain, the square root of the number of people operating in that domain do half the productive work. So you think, well, you have 10 employees, 3 of them do half the work. It's like, yeah, okay. What if you have 100 employees? Then 10 of them do half the work. What if you have 1,000 employees? Well, then it's 30. And if it's 10,000 employees, then it's 100. Here's Price's law. This is something to hammer into your heart. The square root of the number of people in a domain do 50% of the work. Price's law from someone named Derek de Sola Price, who was studying scientific productivity in the early 1960s. And what he showed was that a vanishingly small proportion of the scientists operating in a given scientific domain produced half the output. So it's a tiny number of people that produce almost all of everything. That's Price's law. And technically it is, and I mentioned this to you before, it's the square root law. The square root of the number of people in a productive domain produce half the output. Right? So if you have 10 employees, 3 of them produce half the output. If you have 100, 10 of them produce half the output. If you have 10,000, 100 of them produce half the productive output. Right? It's a very, very vicious statistic. And you won't learn about that in psychology for reasons I have no idea about, because you learn about the normal distribution and not the Pareto distribution. But Pareto.
Since Jordan Peterson is obsessed with order and chaos, he's going to love this next part: order statistics. Suppose we take n independent samples from a distribution and sort them from largest to smallest. Those sorted values are called the order statistics. The first is the largest, the second is the next largest, and so on down to the nth, the smallest. Once we have them in order, we can define something naturally interesting, the top m share. That's the sum of the expected values of the top m samples divided by the total expected sum of all n. It gives us a clean way to ask how much of the total is controlled by the very top few values. Now let's bring the Pareto distribution back into the picture. For a Pareto distribution with parameters x-min and alpha, the expected value of the kth largest sample has an exact form involving gamma functions, generalized factorials. When n is large, to a good approximation, this simplifies beautifully to x-min times n divided by k, all raised to the power of 1 over alpha. That means the top m share can be approximated as a ratio of two sums, each a sum of 1 over k to the power of 1 over alpha. These are the generalized harmonic numbers. So the entire problem of top M concentration reduces to understanding how these harmonic sums behave, and that depends entirely on alpha. When alpha is greater than 1, the Pareto distribution has a finite mean. In this regime, the harmonic sums diverge with n, but the divergence is well approximated by an integral. To first order, the sum from 1 to m of 1 over k to the power of 1 over alpha is approximately m to the power of 1 minus 1 over alpha, divided by 1 minus 1 over alpha. The top m share then simplifies elegantly to m divided by n raised to the power of 1 minus 1 over alpha. Setting that equal to 1/2 and solving for m gives m approximately equal to n times 2 raised to the power of negative alpha over alpha minus 1. So, when alpha is greater than 1, the number of top values holding half the total grows linearly with the sample size. When alpha is less than 1, the Pareto distribution no longer has a finite mean. The largest few values dominate almost everything. In this regime, the harmonic sums actually converge to a finite limit, the Riemann zeta function. That means the total value doesn't keep growing with n. Adding more samples just adds tiny contributions that barely matter. So the top m share equals the partial harmonic sum up to m divided by the full zeta value. If we set that equal to 1/2, the result is an m that is independent of n. In this heavy-tailed, infinite mean world, a fixed number of top values controls half of everything, no matter how large the population grows. When alpha equals 1, we reach a special borderline, the Zipf distribution. Here, the harmonic series diverges very slowly. The total grows like the logarithm of n plus the Euler-Mascheroni constant gamma. That makes the top m share simply log m plus gamma divided by log n plus gamma. Setting that equal to 1/2 gives m equal to e to the power of minus gamma over 2 times the square root of n, about 0.75 times the square root of n. This is the square root case, not a general law, but a knife-edge boundary between two worlds, one with no growth in population size and one in linear growth in population size. A quick detour on gamma, the Euler-Mascheroni constant. It's one of those mathematical constants that seems to pop up everywhere, like pi or e. It's defined as the asymptotic difference between the harmonic series and the natural logarithm, and it shows up across number theory, analysis, and asymptotic approximations, like in our square root scaling. Alright, now back to Pareto. We've now seen how the half-share threshold behaves across the three regimes of alpha. When alpha is less than 1, the number of top values needed to hold half the total stays constant. When alpha equals 1, it grows like the square root of n. And when alpha is greater than 1, it grows linearly with n. This is a phase change in behavior. The square root growth at alpha equals 1 marks the exact boundary between no growth and linear growth. It comes directly from the logarithmic divergence of the harmonic series, with gamma setting the constant factor. But this square root regime is not a general law. It's a very special case, and most real systems don't sit there. If we restrict ourselves to finite mean systems, this boundary almost never occurs in practice.
And this actually turns out to be a rather ironclad rule. It applies across very, very many situations. It applies, for example, to the mass of stars and the size of cities. So you can see how universal it is as a law, and it's something like those that have more get more, and those that have less get less. That's the Matthew principle, right? To those who have everything, more will be given. From those who have nothing, everything will be taken away. And the economists sometimes call that the Matthew principle. And so what that lays out is a world that's rife with inequality. So you hear this idea that I think it's the 85 richest people in the world have more money than the bottom 2 billion. That's a Pareto distribution phenomena. And you might say, to hell with capitalism for producing that. It's like, sorry, you got your diagnosis wrong. It's a natural law. It's no matter what society you study, you get a Pareto distribution of wealth. You get a Pareto distribution of number of records recorded. You get a Pareto distribution of number of songs written or goals scored. Like any creative product has that characteristic. And it's partly because as you start to become successful, let's say, people offer you more and more opportunities. And as you start to fail, people move away from you and you plummet. And so, okay, so that's rough. So what it means is that there is always a landscape of inequality. And I'm not saying that we shouldn't do anything about it, although I am saying that we don't know what to do about it. That's the thing, you know, because you can modify the Pareto distribution of wealth, let's say, but we don't know how to do it without maybe disrupting the system so completely that it collapses, which is what happened in the Soviet Union, for example, and in Maoist China. They were trying, at least in principle, to adjust inequality. But the cure was far worse than the disease. And the truth of the matter is we actually don't know technically how much inequality there has to be to generate wealth. We can guess, and you could say, well, there should be less, and you might say, well, there should be more. If you're left-wing, you'd say less, and if you're right-wing, you'd say, well, we'll just let the inequality flourish. But we do know that it's inevitable, and we also know that we don't know how to regulate it. So, there is inequality. What that means is there's always going to be people around that are better at something than you are. And that's a problem, because you can get jealous and you can get bitter and you can get resentful, and worse, you can get hopeless, you know. So it's a deeply built feature of systems of creative production, and no one really knows what to do about it, because of course the danger is that all the resources get funneled to a tiny minority of people at the top, and a huge section of the population stacks up at zero. But to blame that on the oppressive nature of a given system is to radically underestimate the complexity of the problem. No one actually knows how to effectively shovel resources from the minority that controls almost everything to the majority that has almost nothing in any consistent way, because as you shovel money down, it tends to move right back up, and it's a big problem. Anyway, I understand the catastrophe of the Pareto distribution. I don't like it. You know, there is this proclivity for capital to accrue in the hands of smaller and smaller numbers of people. It's just capital. It's all goods. You get this terrible problem of distribution that's like a natural law. And the fact that people object to that is completely unsurprising. And the fact that if it goes unchecked, it destroys societies I don't think that's a hypothesis. That's demonstrably self-evident. So I especially don't find the compassionate concern for working class people and their well-being the least bit incomprehensible. It's the solutions that are the problem. It's like, well, what should the solutions be? And well, that's where things get very, very complicated.
Before we look at how Dr. Peterson uses mathematical ideas about inequality, it helps us to understand where this framing comes from. A century before Jordan Peterson, long before the rise of modern psychometrics or YouTube lectures, there was Vilfredo Pareto. Pareto was not only a mathematician. He trained as an engineer, became an economist, and wrote as a political theorist. In the 1890s, he made a striking observation. In many countries, a small share of people held a large share of income. This pattern, the concentration of wealth at the top, became the basis of what we now call the Pareto distribution. But Pareto was not a neutral observer of inequality. Born in 1848 to Genoese nationalist nobility in exile in Paris, he was an aristocrat by both birth and conviction. He believed societies are, and always will be, structured around a small ruling elite, and a much larger mass without power or the competence to wield it. For him, this was not a passing condition, but a permanent feature of social life. Pareto argued that efforts to create equality were futile and even dangerous. If one elite is displaced, another inevitably rises to replace it. He called this the circulation of elites. Popular movements, in his view, were simply new elites in disguise, a line of thought Peterson sometimes echoes. This put him firmly against socialism and liberal democracy, which he saw as weak, decadent, and dependent on persuasion rather than strength. When Mussolini's fascism rose in Italy, Pareto welcomed it as a lion elite restoring order. He was sympathetic to the regime and shortly before his death was honorarily appointed to the Italian Senate in 1923. The model he developed was elegant, a simple two-parameter power law that captures many real patterns in data. But real-world distributions are messy. Many are roughly power law distributed, but almost none are exactly. Even so, the pedigree and simplicity give the Pareto distribution a seductive authority. It can feel like a law of nature, clean, universal, and fixed. From the beginning, Pareto's mathematics and name carried anti-liberal and anti-egalitarian political weight. Pareto's ideas didn't stop with him. A generation later, others noticed the same pattern appearing in different domains, even in science itself. Derek J. DeSola Price, a physicist turned historian of science, noticed a similar skew in academic productivity. In his 1963 book, Little Science, Big Science, he proposed what is now called Price's Law. The square root of the number of contributors in a field produces half the output. So if 10,000 people work in a field, the top 100 and the bottom 9,900 each account for half the results. Price attributed this to the way creative and scientific work concentrates. A small group of highly active contributors tends to dominate the literature, while most others contribute only a little. His historical interest reflected his view as well. Price became famous for his work on the Antikythera mechanism, a technological marvel of ancient Greece, identifying it as an ancient astronomical computer, which he interpreted as the product of a tiny, extraordinary intellectual elite. More broadly, he believed that wealth, like scientific activity, naturally concentrates in a few hands and a few places. Price's law roughly matches the Zipf boundary, where the Pareto-shaped parameter alpha equals 1. It is a neat rule of thumb, and it sounds almost mathematical in its precision. But Price's law is not a law in any strict sense, and when tested empirically, it is often wrong. Most Pareto distributions have a shape parameter different from 1. And even when alpha equals 1, the square root estimate overshoots the real number by about 25%. If, and only if, alpha equals 1, the top 75 out of 10,000 account for half. Like Pareto's distribution, Price's so-called law is an idealization, an oversimplified lens on a complicated reality. And because it is so simple, it is easy to mistake for fact or even destiny, which is why it's so useful for inequality apologists like Peterson. This notion that success compounds on itself, that advantage builds advantage, wasn't new. It appears in an older, scriptural register. One of the most famous formulations comes from the Gospel of Matthew, chapter 25, verse 29. For to all those who have, more will be given, and they will have in abundance. But from those who have nothing, even what they have will be taken away. Robert K. Merton borrowed this verse in 1968 to describe what he called the Matthew effect in science. Resources, recognition, and credit accumulate at the top. Eminent scientists are celebrated more, cited more, and rewarded more, often regardless of whether their work is actually better. The result is a self-reinforcing feedback loop. Over time, the phrase has been applied far beyond science, to wealth, culture, education, influence, and power. Inequality compounds, advantage snowballs. But the original biblical verse is not a policy proposal. It comes from the end of the parable of the talents, a metaphor for spiritual gifts, understanding, and responsibility before God, not a lesson about investment or a justification for material inequality. Moreover, Jesus is not any sort of advocate for compounding inequality. Throughout the gospel tradition, Jesus is firmly against gross material inequity. Sell everything you have and give to the poor, and store up treasure in heaven. It is easier for a camel to go through the eye of a needle than for a rich man to enter the kingdom of God. Blessed are you who are poor, for yours is the kingdom of God. The ancient Christian tradition of charity, asceticism, and voluntary poverty pick up directly on this theme, as do modern Christian movements like liberation theology and the social gospel. When modern figures like Peterson cite Matthew 25:29 as evidence that inequality is part of the natural or divine order, they are not just describing a pattern. They are deliberately selecting a theological interpretation that normalizes inequality and ignoring others that challenge it. That scriptural framing made inequality sound timeless, even sacred. But in modern economics, we can measure exactly how unequal a system is, and how those inequalities shift. Power law-like tales appear in many systems, in the masses of stars, in the sizes of cities, and in the distribution of wealth. But they are not all the same distribution. A tail with alpha near 2 behaves very differently from one with alpha near or below 1. One has a finite mean and moderate inequality. The other is extreme and top-heavy. How the larger values balance dynamically with the smaller ones, as both grow and shrink over time, determines the shape of the overall distribution. Pareto distributions describe how a system behaves, but they do not explain why. They are descriptive, not prescriptive. The current shape of the distribution is not an inevitable law of nature that must stay fixed forever. Economists have long known that the distribution of wealth is constantly in flux. Wealth ebbs and flows. Inequality rises and falls. Alpha is never fixed. It reflects structural forces, capital accumulation, inheritance, taxation, technology, redistribution, and public goods. A larger alpha means a lighter tail, less top concentration, and a lower Gini coefficient. A smaller alpha means heavier tails, more concentration, and more inequality. When people talk about changing the distribution of wealth, what they are really talking about is changing alpha. This is not about violating natural law. It is about political and social structure. Alpha can and does change over time, and can be shaped through policies and institutions. This brings us back to Peterson, who often takes the Pareto pattern not as a flexible structure, but as an iron law of nature, a kind of deep, harsh wisdom about reality. Jordan Peterson often says he understands the catastrophe of the Pareto distribution. He tells audiences that he does not like inequality, but that we don't know what to do about it. He warns that the cure is worse than the disease, claiming that getting inequality even slightly wrong can lead to red terror, dekulakization, and gulags. Peterson argues that it is futile to shovel money down the hierarchy because it will just flow back up. He says that some people can ride the wave of the Pareto distribution, that success breeds success, failure breeds failure, and that this is exactly what the Matthew principle describes. This fits a rhetorical pattern he often uses, positioning himself as the reluctant bearer of a harsh, catastrophic truth. By presenting inequality as a terrible but immovable fact of nature, he casts himself not as an ideologue, but as a brave truth-teller willing to look at hard realities others can't face. This allows him to smuggle in an ideological commitment while denying it's ideological at all. But that story leaves a lot out. Success and failure are shaped by structural factors like parental wealth, education, nutrition, healthcare, networks, and geography. Luck and circumstance matter, and fortunes can rise and fall over time. Peterson himself has lived through periods of both success and decline. Inequality is not determined solely by personal virtue or by some natural law. Peterson tends to focus on psychometric traits like intelligence or conscientiousness, which shifts the conversation away from material factors. And whether or not he intends it, that framing is friendly to far-right interpretations. It casts inequality as natural, normal, and inevitable, something like a law of nature, and resistance to it as naive or dangerous. But as we've seen, none of that follows from the math. The 80-20 rule or square root rule corresponds to just special cases where alpha equals 1 or 1.16. Most systems do not sit there, and nothing says alpha cannot change. Power law-like tales are empirically common, and Pareto distributions are mathematically elegant ways of describing them, but they are also politically loaded. Pareto himself saw inequality as natural and inevitable. The Matthew principle gives it a moral, even divine frame. And Peterson and others use it as propaganda to make inequality feel like fate, something we challenge at our peril, in opposition to both nature and Christ. But the shape of today's wealth distribution is not fixed. It reflects human structures, incentives, and choices. When someone says inequality is inevitable, they are not citing a theorem. They are making an ideological argument wrapped in the language of math, often without real mathematical competence. The Pareto distribution describes patterns, it does not justify them. And we can choose, through policy, structure, and collective action, to build a more just and equal world, rather than accept as fate a world of oligarchy, elitism, feudalism, authoritarianism, or capitalist hegemony. For Peterson, the Pareto distribution shapes how he sees the political landscape. He accepts what he views as the hard but inevitable truth of fewer and fewer people holding more and more of the total wealth, a fact that, in his framing, can only be questioned out of ignorant naivete or resentful Marxist murderousness. For Peterson and other rightist apologists, inequality and hierarchy are ideological axioms, playing the role of natural or divine laws. And the Pareto distribution, Price's law, and the Matthew effect function as their pseudo-intellectual cover.
Pareto, this could be Pareto.